All right, this is the third of 3 videos where I'm going through the word problems of practice test 2. This problem is question 7 on the practice test. Question 7 attracted a question from someone that's looking at the problem and noticed that there was no initial bacteria in the tank from this line here. Finally, assume the initial amount of bacteria in the tank is 0, and had noticed that there is no flow in or out of the tank, but somewhere we're getting bacteria. So I guess there's a few ways you can look at this, but frankly, the problem's a bit unrealistic. And like questions 6 and 5, these are highly simplified versions of real world problems. I mean, essentially, what you've got to do to generate one of these problems is take an ODE that a first year is capable of solving, and then shoehorn a physical interpretation upon it, so bacteria and tank, for example, that kind of makes enough sense that you can work with it. In this case, what we've got is we've got a tank. There's some sludge at the bottom of the tank. And this sludge is apparently producing bacteria. So there's a bacteria popping out. There's another bacteria popping out. Stuff like that, right? It's somewhat unrealistic to have this, right? This is, it primordial sludge theory, I guess, says that this could have happened at some point. You've got a chemical reaction complex enough in a soup that produces multicellular life, but it's highly unrealistic. You can, I guess, if you wish, instead of saying bacteria, you can say harmful substance, and so on, right? And just assume that it's not cellular life, it's some chemical that's being produced by a reaction in the sludge. So, if you've got a reaction, right, in the sludge, you can have no initial product for that reaction. You just need the reactant present. So I guess that's how you view this problem, that this sludge can become a source of bacteria or harmful substance in the tank. Okay, so let's now attempt to solve this problem. Let x of t be the amount of harmful substance in a water tank at some time t. That gives us our dependent and independent variables. Our independent variable, the coordinate, if you like, is time. The dependent variable, the thing that depends on the independent variable, is x of t, the amount of bacteria. Because we want to build an ODE model, we know that we're going to be getting something like dx dt equals stuff, right? And we've got to figure out what that right-hand side is and then move on and solve the equation. So we're given a bit of information about the right-hand side. We've got a chemical that removes bacteria, right? So we've got some removal term. We've got a negative contribution to this rate. So removes bacteria from the water at a rate proportional, right? So removal and rate means that we've got some contribution to dx dt. So we've got a removal term, and we've got to determine what that removal term is. right? Because it's removal, it's a negative contribution to the rate of change of the bacteria in the tank. So it's going to be negative. It's going to have a minus sign in front of it. So let's read this. At a rate proportional to the amount of bacteria present at any instant in time, right? So that means amount of bacteria present at any instant in time, that's x of t, right? Or harmful substance, or whatever we've decided to call this x of t interpretation. So we've got an x of t term here, but there's more information. But the efficacy of this removal, so how good it is at removing the harmful substance or the bacteria or whatever we've got, of the chemical decays in time like 1 over t. So we've got some proportionality constant. We've got a 1 over t function representing the fact that this chemical is losing potency. So let's go with A over t. So that's our A is our, the sort of constant of proportionality. The 1 over t term's in there because that's representing the decay of the efficiency of this chemical. And it's all multiplied by x of t because the chemical removes bacteria at a rate proportional to the amount of bacteria present. And the constant of that proportionality isn't really a constant. Instead, it changes in time, like 1 over t. Okay, so that's our removal term. The next sentence, also suppose that the bacteria in the tank increases at a linear rate in time. Now, that means that we've got an introduction term, we've got a source term, if you like, of bacteria. And it's linear in time. So linear means it's a t function. It's not a t squared. It's not a t to the power of a half. It's just a t function like this. There's no mention of, like reproduction of bacteria. So this introduction doesn't depend on x in any way. So all we've got's t. And we've got that this could be any rate of increase. So if we've got a sludge that's, quite good at producing this harmful substance, we want to be able to represent that as opposed to a sludge that's not very good at representing this, producing a substance. So we've got some constant multiplier b. Now that just says that it's that just sets the rate. So if b is large, that's obviously producing bacteria faster than if b was small. Finally, assume that the initial amount of bacteria in the tank is 0. Well, that just tells us an initial condition. Right, so our rate overall, we've got a removal and we've got an introduction. So our ODE problem becomes dx dt equals minus a over t x t plus, because the introduction's positive, b t, like so. Right, with this initial condition, we've got enough information to solve this problem completely. This is a first order linear ODE, so we rearrange the canonical form. We identify our functions p and q, that's sort of our common terminology for the canonical form, and we write down our integrating factor. All right. I'm just going to jump to what the integrating factor is. If you want the intervening steps, see the second video in this series. So if you're watching them in order, this is the third video and you should already know how to do this. So let's write down our equation multiplied by our integrating factor. Oops. All right, now we can use what's loosely described as the reverse product rule. Right, we know, we've seen this in lectures, we know that this is always going to happen by the choice of our integrating factor. We chose our integrating factor, so that that equation must be true, that this term here equals the thing above the red brace there. This gives us a directly integrable ODE. We can now integrate both sides with respect to t. The left-hand side is easy. We just that just gets rid of the d by dt. The left-hand side, we add 1 to the power and divide by the new power. We also need a constant of integration, so we can put that on the right-hand side now. We can apply our initial condition at this point, so we substitute in. So obviously, when t is 0, the left-hand side is 0. When t is 0, that first term is 0. You know, you got this b divided by a on 2 times 0, and then you got a c, right? So in this case, c is 0, and our overall solution is x of t equals, so we just plug it back in here. Then we can rearrange for x just by dividing by that t a. And when we do that, we'll find that we get this t squared function overall here. All right, so that's the particular solution in this case.